Hello learners, welcome to this second lecture on alternating current. In your last lecture we have gone through different topics related to alternating current, like what is root mean square, value of current, what is the peak value of current, what is alternating circuit with resistor, what happens inductor is there in a circuit, what will be the behavior of the current or circuit when a capacitor is introduced, and so on and so forth. Today we will deal with alternating current circuit with series LCR circuit. What is resonance, what is quality factor, graphical relation between frequency versus inductive reactance and capacitive reactance, power in LCR circuit, and what is called as wattless current. So let us go through what will happen whenever there is an alternating current flowing in a circuit containing inductance, capacitance and resistance in series. Here you see this is an inductor having self-inductance L, a capacitor having capacitance C, and a resistor having resistance R. All are connected in series LCR, hence it is called as LCR, series combination or series circuit. To this is connected a source of alternating current represented by this symbol. Across LCR is connected your source of EMF given by E equal to E0 sin omega t. E0 is the peak value of the EMF, omega is the angular frequency. So EMF applied is here alternating in nature, and the applied EMF appears as voltage drops here across the resistance, inductance and capacitance. Here when it is connected, when the source of EMF is connected across the circuit, a current is flowing through the circuit, and that current how changes the induced EMF, that we will discuss here. The applied EMF appears as voltage drop VR, VL and VC across resistance R, inductance L and capacitance C respectively. And here in resistance the current and voltages are in same phase. We may calculate, if you calculate in detail in the final expression, we can find here how current is also related to this sin omega t. And finally we can come to the conclusion here that in resistance current and voltages are in same phase. So in the phase diagram, vector diagram you write, you may represent here current I and voltage VR along the same line. But if the circuit is purely resistive circuit, in your last class you have seen, if the circuit is purely resistive circuit, voltage or EMF and current are in same phase. In your previous lecture it has been discussed in detail. And if it is a purely inductive circuit, in circuit containing inductance only, current lags behind voltage by pi by 2. So angle between voltage and current, it is pi by 2. But if it is purely a capacitive circuit, then current leads the EMF. Current leads the EMF. It is represented by this figure. VC represented by this green line vector, VL represented by this violet line vector. Okay, so this is the vector diagram. So in this case what happens? It is neither purely inductive nor purely resistive nor purely capacitive, but it is a combination of all these three. So whenever it is a combination of all these three, here you see this is VC, right? This one is VL. VC is lagging behind. So what is the result? VL minus VC. Resultant vector is VL minus VC. This one. VC, when deducted, this portion represented by this arrow, it will be VL minus VC. And that VL minus VC now represented in a separate figure in the vector diagram. This is I and R. And these two lines, VR and VL minus VC, forms the sides of a parallelogram whose angle is 90 degree. So resultant is diagonal of the parallelogram. means it is a rectangle, resultant is the diagonal, and that resultant EMF is E. And applying your Pythagoras theorem, E will be equal to square root of VR square plus square of VL minus VC whole square. And here you see the resultant EMF depends upon the individual voltage drops across resistance, inductance and capacitance. So that is resultant EMF E, and direction of the resultant EMF, it is given by this angle phi. It is given by this angle phi. Why? Here you see phi is the angle between I and E. That is the phase difference between applied EMF E and the current flowing through I. According to Ohm's law, current equal to EMF by net impedance. Here square root of R square plus XL minus XC whole square, it is the net opposition offered by this LCR circuit. So we say it is the net impedance. So current flowing through the circuit will be given by I equal to E division square root of R square plus XL minus XC whole square. This impedance is sometimes it is represented by Z. Okay, it is given by Z. So in sometimes numerical problem are maybe given, XL, XC will be there and you will be asked to calculate what will be the value of the impedance. So there should be no problem in calculating what will be impedance. It will take the unit in SI as ohm, right? Whether it is impedance or it is inductive reactance or it is capacitive reactance, it is measured in ohm. And inductive reactance is omega L, omega is the angular frequency, capacitive reactance is 1 by omega C, here omega is also an angular frequency. And from this figure, vector diagram, you may find what is the phase angle. You find tan phi. Tan phi will be equal to VL minus VC by I. It will be VL minus VC by I. If you solve that, it will be this value, XL minus XC, because VL will be current I into XL minus XC. Here V equal to IR. So resultant tan phi will be equal to XL minus XC by R. So from this also, this figure you may find out cos phi, which we will later on discuss it as power factor, right? That will be discussed as power factor, and that power factor may be also expressed in terms of XL and XC. Again, XL may be replaced by omega L as well as 1 by omega C. So tan phi equal to XL minus XC by R means it is equal to omega L minus omega C by R. So let us see that phi as well as net current, as we have discussed earlier, depend upon the relative value of XL and XC. I depend upon XL and XC, phi depend upon XL and XC. So what will happen depending upon the relative value of XL and XC? Let us discuss some special cases. You see here, okay, you see here that when XL is greater than XC, inductive reactance exceeds the capacitive reactance. At that time, this XL minus XC is positive, means tan phi is positive, means phi is positive. So at that time phi is positive means current lags behind the EMF by phase angle phi. Current lags behind the EMF by phase angle phi, and the LCR circuit is inductance dominated circuit. At that time we may say LCR circuit is inductance dominated circuit. But when the reverse thing happens, when inductive reactance is less than capacitive reactance, that is to say omega L is less than 1 by omega C, then what will happen? Tan phi is negative. So it implies phi is negative, that is current is leading the EMF by an angle phi, and the LCR circuit is capacitance dominated circuit. Remember, when XL is more than XC, inductive reactance is more than capacitive reactance, it is a inductance dominated circuit. When inductive reactance is less than capacitive reactance, it is a capacitance dominated circuit. Well, let us see the third case when both what are these? reactances, when both the reactances are equal. When inductive reactance is equal to capacitive reactance, XL equal to XC, means tan phi will be equal to 0 by R, means tan phi will be equal to 0, so phi equal to 0. No phase difference between current and EMF. Then we say the current and the EMF are in same phase, and the impedance does not depend upon frequency or the applied EMF. Why? XL equal to XC means impedance Z will be equal to R. At that time, if you put the value of XL minus XC equal to 0 in the expression for Z equal to square root of R square plus XL minus XC whole square, then obviously we will get Z equal to R. So impedance is independent of XL and XC, means it is independent of frequency of the applied EMF, and at that time the LCR circuit behaves purely as a resistive circuit. That means even if at that time inductance and capacitance will be there, it will have no effect. So from this expression, that discussion that we have seen, that when XL equal to XC, then omega L equal to 1 by omega C, and we know omega equal to twice pi f, f being the frequency. F being the frequency, then your impedance is minimum, that is Z minimum equal to R, and at that time whenever opposition is minimum, impedance is minimum, then current is maximum, peak current is maximum, that is E by R. So impedance offered by the circuit is minimum and the current is maximum, and when current or flowing through the LCR circuit is maximum, then we say this circuit is at resonance, or this condition is called a resonant condition of LCR circuit, and at the time the frequency will be said to be resonant frequency. So let us calculate what is the resonant frequency. So it will be governed by this condition, XL equal to XC or omega L equal to 1 by omega C. As it is the frequency at resistance, that omega will be replaced by omega R, resonant angular frequency. So at resonant angular frequency, omega R L equal to omega R 1 by omega R C, or omega R equal to 1 by square root of LC. Solving this equation, omega R, what is omega R? 2 pi FR, already I had told to you, 2 pi F, omega R means 2 pi FR. So 2 pi FR, here 2 pi FR, okay. Or simply omega R equal to 1 by square root of LC, put omega R equal to 2 pi FR, solve it, you will get FR equal to 1 divisions 2 pi into square root of LC. So this is the expression for resonant frequency. From this we may ask problem, L and C may be given, and we will be asked to calculate what is resonant frequency. And now let us discuss what is resonant curve and Q factor. Suppose our frequency, angular frequency is along x-axis and peak value of current is along y-axis. We may draw graph showing variation of I0 with omega, which will be of this curve shape having a peak here. Okay, this is for a particular resistance R1. Here you see the current increases with the increase in angular frequency, becomes maximum at a particular value of frequency, and that frequency is called resonant frequency. That current will be called resonant current. Resonant current will be corresponding to this position as I am showing in the cursor. Correspondingly, resonant frequency will be a frequency here at the middle, and this is for one resistance R1. It may be represented for other resistances, maybe a lower or a higher value. Here you see three different resistances we have shown, R1, R2, R3, such that R1 is less than R2 is less than R3. Whatever it may be, R1 is the maximum resistance, R3 is the, here R1 is the minimum resistance, and R3 is the maximum resistance. When resistance, for more resistance, what we say, R1 is less than R3, means R3 is greater than R1. So peak becomes flat. Here it is something less flat, means more sharp. Here it is more sharp. For low resistance, generally the curve is a sharp one, whereas for other cases, you see what is the nature of the curve. Also, If resistance is low, peak current is more. If resistance is gradually increasing, peak current is decreasing. So that this curve is also called as frequency response curve. Here we see, just we have marked, this is I0 maximum corresponding to resonant frequency omega r, and here we may see that for a particular value of frequency at which maximum current becomes 1 by root 2 times I0 maximum, it corresponds to certain frequency. Those frequency will be called as sideband frequency, corresponding to this point and corresponding to this point. And this width omega r left, you see to the left side of omega r, and here the frequency corresponding to this point will be omega r minus del omega, means this particular width. Gap between green dotted line and pink dotted line is del omega. Here also it is del omega. So separation is 2 del omega here, and in between the two frequency, one sideband frequency will be given by omega r minus del omega, the other is omega r plus del omega, but both corresponds to the same value of current I0 by root 2. And here this 2 del omega, it is called bandwidth. It is called bandwidth. And here quality factor or Q factor, it is defined as the ratio of resonant frequency to bandwidth, omega r minus omega r division 2 del omega. Your Q factor or quality factor Q equal to omega r division 2 del omega. Omega r may be 2 pi fr, where fr will be your linear frequency. Also quality factor is nevertheless may be defined as the ratio of potential drop across the individual inductance or the capacitance to the potential drop across the resistance. It is the ratio of the potential drop across either the inductance or the capacitance. If it is inductance, it will be VL by VR. If it is capacitance, it will be VC by VR. So it will have no unit, being the ratio of two voltages. You may substitute VL as omega RL. So Q will be equal to omega RL division R. Correspondingly, substituting for VC, it will be Q equal to 1 by omega RC R. Okay. So these are quality factor. Now, what is the power of a circuit that contains inductance, capacitance and resistance in series? It is the power. What is power? Power is the rate at which energy is consumed. And you know, instantaneous power, it is the product of potential difference or EMF and current I. The instantaneous EMF, being alternating in nature, will be given by E equal to E0 sin omega t, and suppose current at that instant is I0 sin omega t plus phi, where phi is the phase difference between EMF and current, or you may say phase angle between EMF and current. So let us substitute this E here and this I here. Correspondingly, you will get E0 I0 sin omega t plus phi. Expand sin omega t plus phi in the next step. It is in the form of sin A plus B, that is sin A into cos B plus cos A into sin B. Sin A into cos B plus cos A into sin B. Here it is sin omega t into cos phi plus cos omega t into sin phi. Now multiply this sin omega t into every term, with every term of the bracket. First with sin omega t cos phi, it is sin square omega t cos phi. Then sin omega t multiplied with cos omega t sin phi, it is sin omega t cos phi. Here you see this sin square omega t may be represented in terms of cos 2 omega t. And this sin omega t cos omega t, it is may be represented as in the form of sin 2 omega t. So these may be expressed as you may say sin 2a or cos 2a form, and we may at that time simplify this expression. So if the instantaneous power is consumed here and it is constant, say for any small interval of time dt, then what will be the work done? Here you see instantaneous power is the rate at which work is done. You know, Instantaneous power is the rate at which work is done. So dW by dt will be this much. This is not only dW. This is the work done in 1 second in a small. So dW by dt is taken as here 1 second, or dW will be equal to E0 I0 into this quantity into here in the cursor mark there should be dt. In the cursor mark there should be dt. It is not there here. Somehow it is just left here. There should be dt because power, it is the rate at which energy is consumed. Here it should be power equal to dW by dt, or dW equal to this into dt. Okay. So if you integrate this expression, you may get what will be the work done over a complete cycle. So right hand side will be integrated in between time 0 and time period t. After integration, if we substitute the upper limit and lower limit, as I had told you, integration may be performed using sin 2a formula here, cos 2a formula here. Final expression is E0 I0 cos phi into t by 2. Okay. And in a similar way, we may calculate what is the average power over a cycle. Generally, average power over a cycle should be W by T, as we know from our previous idea. Power consumed will be equal to W by T. And here you see power consumed equal to W by T. This is W, substitute here. This W may be substituted here. T will go out. So it is E0 I0 by 2 into cos phi. E0 I0 by 2 into cos phi. Now let us rearrange this. This 2 may be root 2 into root 2. So average power consumed over a cycle is E0 by root 2 into I0 by root 2 into cos phi. And here, you know, already I had told to you, cos phi, it is called power factor. It is the ratio between resistance to impedance of the circuit, and for LCR circuit, impedance is given by square root of R square plus omega L minus omega C whole square. So this one is the expression for your power factor. Okay. Now here you see average power, it is the product of E0 by root 2. You see it is the RMS value or virtual value of EMF. I0 by root 2 is the RMS value or virtual value of current. So average power consumed is EV IV cos phi. So it is the factor cos phi which is governing the average power, or upon which average power depends. Hence it is called as power factor. Suppose cos phi is 1, then average power consumed is maximum. Cos phi is 1 if phi is 0 for a purely resistive circuit. If cos phi is 0, cos phi 0 means pi by 2. For inductive circuit and capacitive circuit, cos phi is 0, power factor is 0, so average power consumed at the juncture will be 0. Now, nevertheless, here we may represent this in this particular way, this discussion to repeat it again. In resistive circuit, current and EMF are in phase, so that phi equal to 0, so average power is maximum, as already pointed out. EBIB cos 0, that is equal to EBIB. For power of inductive circuit, no power is consumed, no watt is consumed. Okay. And in capacitive circuit, also phi equal to pi by 2. For inductive it is minus pi by 2. Here also no power is consumed, no watt is consumed. And in this connection, let us go through what is called as wattless current. What is called as wattless current or idle current. Here we see if phi is the phase angle between virtual value of EMF and current, at the time here you see in the vector diagram, IV will have two components, IV sin phi, IV cos phi. And the component IV cos phi, here it is there in the expression for power. Okay. But the component IV sin phi, it is not there in the power component, so it will not contribute to power along EV. Hence power generated is 0 if it is not contributing. And this component of current, which component? IV sin phi, it is called wattless or idle component because it is not contributing in the expression for power. Okay, so at that time, here you may say IV sin phi represent wattless or ideal current. So now if it is 90-degree angle between these two, you mark in the figure IV sin phi. Here IV sin phi is there, cos phi is 90-degree, then no power is consumed. So corresponding to the current, power consumed will have no watt. It is wattless. Okay. So power is not dissipated if phi is 90-degree. Means if it is a inductor or if it is a capacitor, no power is expended, no power is consumed. Hence, they find a lot of practical applications and in devices using alternating current. Okay. So this is how we can explain what is wattless current. Now, what is LC oscillation? Let us have a brief discussion. If a circuit contains inductance and resistance here, then correspondingly here you see in the beginning potential energy is maximum due to electric field is maximum, and that due to magnetic field is zero. After interval of t by 8 time, what will happen? Both energy due to electric field and magnetic field will balance each other, and here we are showing in the figure in what will happen at t equal to 2t by 8. Energy due to electric field is nothing, and that due to magnetic field is maximum here. After 3t by t, again ue equal to ub. So all these are experimental finding. You see what is the variation after different intervals of time. After different intervals of time, you see variation, and in this case due to this variation, the circuit is set into oscillations. One part of the plate here is positive, here it is negative at when ue equal to ub, but when the electrostatic potential energy is zero, energy due to electric field is zero, here you see the capacitor plates. So in this particular case, here we will say oscillation will take place in a circuit called LC circuit containing inductance and capacitance. Generally, we may say it to tank circuit, and when the amplitude of oscillation remains constant with time due to flow of charge through it, it is called undamped oscillation. But when the amplitude of oscillation gradually decreases with time, it is called damped oscillation. Here you see in the first figure, undamped oscillation is represented by equal amplitude both in the positive half as well as in the negative half. But in case of damped oscillation, amplitude decreases with time, decays with time. And if Q be the charge on the capacitor at any instant small t, and di by dt is the rate of change of current, then for LC circuit, your L di by dt plus Q by C will be equal to 0. That is the equation. But I equal to dq by dt, if you put here I equal to dq by dt, which is the induced EMF in the circuit, which is equal and opposite to the capacitive circuit, so resultant will be 0 here. So I equal to dq by dt means it will be d square q by dt square. So L d square q by dt square plus q by c equal to 0. Now dividing both right hand side and left hand side by L, you will get d square q by dt square plus q by LC equal to 0. And let us substitute 1 by LC as omega square. So finally the equation reduces to d square q by dt square plus omega square q equal to 0. And here this equation d square q plus dt square plus omega square q equal to 0, that is the final equation. It represents an equation of simple harmonic motion. So definitely the LC circuit executes simple harmonic oscillation with frequency omega given by 1 by square root of LC. As you have taken omega square equal to 1 by LC, as omega equal to 2 pi f, substitute 2 pi f here, frequency of oscillation of LC circuit or tank circuit will be given by f equal to 1 by 2 pi LC. Okay, so that is tank circuit, that is LC oscillation. How oscillation takes place? All about this we have discussed. You may ask question, what is damped oscillation, what is undamped oscillation, and you knowing L and C, one can calculate what is the frequency here. And now, basing upon the chapters that we have taught, let us solve some numerical problem. Here one such problem is, a field of 0.125 Tesla is perpendicular to a coil of area 5 into 10 to the power minus 3 meter square with 1000 turns. It is removed from the field in 0.05 second. Calculate the EMF induced. So, you know the formula for induced EMF is E equal to minus d phi V by dt. And here given values are B equal to 0.0125 Tesla, A equal to 5 into 10 to the power minus 3 meter square, number of turn N equal to 1000, and if phi 1 and phi 2 be the magnetic flux linked with the coil inside and outside the magnetic field, then what will happen to phi 1? NBA. For 1 turn it is BA, it will be NBA. Substitute the value for N, for B and for A, right? This is the value, and if you calculate, this value is 625 into 10 to the power minus 4 Weber in the beginning, and finally it will be 0 when it is taken out. Okay, when it is removed from the field, phi 2 will be 0. So change in magnetic flux is phi 2 minus phi 1. It is 0 minus 625 into 10 to the power minus 4. That is minus 625 into 10 to the power minus 4 Weber. So induced EMF E equal to minus d phi by dt. Substitute d phi and dt. This is the value. Okay. So it is minus 625 into 10 to the power minus 4 divided by 0.05 volt. After calculation, resultant value is 1.25 volt. That is the induced EMF produced. Okay. Another problem, the current in a coil drops from 10 ampere to 2 ampere in 0.1 second. An average EMF of 32 volt is induced in the coil while this happens. Calculate the inductance and inductive reactance of the coil if frequency of alternating current is 50 Hertz here. So given induced EMF is 32 volt, time is 0.1 second and frequency is 50 cycle per second or 50 Hertz you may say. A change in current DI should be final current 2 ampere minus initial current 10 ampere, that is minus 8 ampere. Now as per our previous discussions in electromagnetic induction chapter, induced EMF E equal to minus L di by dt. Substitute the values of the corresponding quantities. 32 equal to minus L into minus 8 by 0.1. It will yield L, self-inductance or coefficient of self-inductance is 32 by 80. That is approximately not approximately, rather exactly 0.4 Henry. So that's the value of self-inductance. So what is inductive reactance then? It is 2 pi FL. F is given here 50 cycle per second. Substitute the value. So resultant inductive reactance will be 125.6 ohms after calculation. If the circuit contains capacitor, sometimes you may be asked a problem to calculate capacitive reactance. Instead of the value of L at the time, capacitance C will be given, and correspondingly you may calculate capacitance of the circuit. Another numerical example here, that it is the current in a coil drops uniformly to 0 in 0.0001 second in the primary of an inductance coil of mutual inductance 5 Henry. An EMF of 30,000 volt is produced or induced in the secondary when break occurs. Calculate the current in the primary before the break. Now let us solve it. Here it is given that induced EMF equal to 30,000 volt, time equal to 0.0001, means it is 10 to the power minus 4 second. Mutual inductance is 5 Henry. Again, as per principle, E equal to minus M di by dt. Substitute the values. For E 30,000, for di we have to calculate what is di. Here dt is 0.001, so this will give change in current as minus 0.6 ampere. But if I is the initial current, then change in current di should be 0 minus I, which we have calculated as 0.6 ampere. So I minus I equal to minus 0.6, so I equal to 0.6 ampere. So the current in the primary before break is 0.6 ampere. Another interesting problem, let us cast a glance on it. The equation of an AC is I equal to 50 sine 400 pi t. What is the frequency and RMS value of the current that you have to calculate? It is a very simple problem. Just you should have to compare this with the general equation of alternating current. Here I is given. In some other cases EMF may be given. E equal to 50 sine 400 pi t. Same procedure you have to add up, you have to follow. So here which quantities are given? Given I equal to 50 sine 400 pi t. So let us rearrange it. This 400 pi t may be rearranged as 2 pi into 200 t. Now let us compare this equation with the general equation for alternating current for its instantaneous value y equal to I0 sine 2 pi ft, f being the frequency. And by comparison of these two equations, here you see in this problem I0 corresponds to 50 units. If it would have given in SI, we might have written 50 ampere. Okay, f is 200 hertz. Why hertz? Nothing is given, because cycle per second or second remains same whether you are taking CGS unit or you are taking SI unit, right? So f is known, I0 is known. What is the virtual value or RMS value of current? It is I0 by root 2. If it is I0 by root 2, put I0, if it is 50 by root 2, after calculation it is 35.36 seconds. So this is all about the discussion today. You may calculate more and more problems. The more problem you work out, the more efficient you will be. So do that, enjoy that, do your problems, as many problems as possible, so that you can be much more brilliant. You can clear all your fundamental by greater amount. So for today, thank you very much. Have a happy learning.